Hey guys, this is David. In the previous lecture, we have learned how to formulate the constraint equations for revolute joints. In this lecture, we will move on to translational joints. In order to help you to understand what translational joint is like, here are some common translational joints that you can see in planar mechanisms. For example, in this mechanism, this slide and this bar are connected by a translational joint. In other words, the slide is translating on the bar, and we will usually define a so-called translational axis like the purple dashed line to indicate the translational direction of the slide. And for this example over here, this slide is translating on the ground, and the translational axis is the dashed line shown here. It is suggested that you pause the video first and make sure you do understand the concept, because this is a very important step before we move on to the mathematical derivation. Okay, so now it's time for the mathematical part. First, let's recall what we have learned in the first lecture. That is, a translational joint will reduce 2 degrees of freedom of the system. The equivalent expression is a translational joint will provide 2 constraint equations to restrict the motion of the system. The first equation is position constraint, because if the slide had to always be on the translational axis, it is obvious that the position of the slide must follow some rule. Just like the y position of the slide here must always be equal to yc, since it's translating on the ground. The second equation is angle constraint. Since the slide is translating on the ground, it is clear that the slide cannot have relative rotation with respect to the ground, which means that the angle difference between the slide and the ground is a constant, just like the 0 here. Don't worry if you cannot come up with these 2 constraint equations right now. After watching this lecture, you'll realize how easy it is to derive them. In the following slides, the mechanism on the right will be used as a general example to show you how to derive the 2 constraint equations. In case you cannot picture the motion of this mechanism, it is identical to the mechanism on the left, which looks like this. Therefore, it is obvious to tell that rigid body 2 is translating on rigid body 1, and the translational axis is the purple dashed line shown here. And since now we are using Cartesian coordinates, we have to define the global coordinates of the system and the local coordinates of each rigid body. Here, I have set the origin of the global coordinates at this point, and the origin of the local coordinates of rigid body 1 at this point, which I assume to be the mass center of rigid body 1. And next, I define theta 1 to be the angle difference between the local coordinates of rigid body 1 and the global coordinates. As for rigid body 2, its local coordinates are defined as this. Do notice that the reason why I didn't draw out the local coordinates for the bar over here and for the ground is because we won't rely on them when deriving the constraint equations for translational joint. Okay, I think now we are ready to move on to step 1. Define a fixed point in the local coordinates of rigid body 1 that is on the translational axis. Here, I have defined point A to be a fixed point in the local coordinates of rigid body 1. This means no matter how rigid body 1 rotates, point A will always be on the translational axis. Also, since point A is a fixed point in the local coordinates of rigid body 1, We can express the position of point A using coordinate transformation as shown as the equation here. Great! Now let's move on to step 2. Define two fixed points in the local coordinates of rigid body 2 that is on the translational axis. Basically, this step is almost the same as step 1, except that now these 2 points are fixed points in the local coordinates of rigid body 2. Again, this means that no matter how rigid body 2 rotates or translates, these 2 points will always be on the translational axis, and that we can express the position of these 2 points using coordinate transformation. Okay, step 3. We are now ready to derive the position constraints. The trick is that since these 3 points A, B, and C are always on the translational axis, which in other words means that they are always on the same line. Therefore, the slope of vector AB will always be identical to the slope of vector BC. With this geometric property, we will be able to come up with the position equation shown here. However, do notice that when the angle of the slope is equal to 0 or 180 degrees, the denominator is 0. But it is clear that we cannot have division by 0. Therefore, in order to avoid this, I cross-multiplied the equation, and what we will end up with is the equation right here. Last, for the angle constraint, since rigid body 2 is translating on rigid body 1, this means rigid body 2 will not have relative rotation with respect to rigid body 1. In other words, the angle difference between these two rigid bodies will always be a constant. Or, to be more specific, will always be the angle difference between the local coordinates of these two rigid bodies before the mechanism starts to move. Here, I let theta 1 init and theta 2 init to be the angle of the local coordinates of these two rigid bodies before the mechanism starts to move. And with these two variables, we can come up with the equation shown here. Great! So this is how we derive the constraint equations for the translational joint.